Hi everyone, and welcome to our screencast about the basics of waves. So the last week I had you do exercises with the waves on the string and read some things in the book. So today I just wanted to go and make sure that we all picked up on some of the important things about waves from the activities. So all waves are made by something moving back and forth. There's some sort of vibration, and the book reading made a big deal about that, something moving to and fro. So it can be a person's hand moving a string or a spring or something like that. In a musical instrument, it could be a reed vibrating back and forth, or a string that is plucked that is vibrating, or all sorts of things. And so there really are two different kinds of waves. And so first thing I want to do is show you a short video about that illustrates that, so you can see it live. And so here we go.
Today I just want to show you a demonstration of transverse and longitudinal waves using a slinky. Now, transverse waves, the direction of energy is going to be going forwards, and that's the same with longitudinal waves as well. The energy is going to go this way. But with a transverse wave, the medium, so in our case the slinky, which is what the wave is going to travel through, is going to be moving perpendicular to the direction of energy transfer. So let me give this a go. So you can see the pulses or the waves are moving from the left to the right. So the energy is moving from the left to the right, but the actual slinky itself is moving perpendicular to the direction. Now another kind of wave is a longitudinal wave. Now with a longitudinal wave, the medium, again which is the slinky, moves in the same direction as the energy transfer. So the energy is moving in this direction, our wave is going to be, or the medium, the slinky, is also going to be moving in this direction. So this is a longitudinal wave, like sound is also a longitudinal wave. So in this case you can see that there's a part where the wave gets compressed and a part where the wave gets rarefied, and that these pulses move along in the same direction that the energy is flowing. So that's a longitudinal wave, like that. That's a transverse wave. Okay, bye for now.
Okay, so that was a good demonstration here. So a couple things about the waves. These have parts. So we want to think in terms of, so if you have a wave that you're making on a slinky or a string or something like that, there's kind of that rest position, which would be like right here. Okay, there are several parts. So the top here is called a crest for a transverse wave. The bottom is called a trough. Okay, and notice the movement of the hand. So the hand is moving up and down. So if you look at one piece of string, one point on the string, it moves up and down, but the wave itself travels sideways. So transverse waves, the medium is what we call what it's moving through. So the medium moves perpendicular to the direction the wave travels. Medium moves perpendicular to the direction the wave travels. So the wave is traveling this way. Sideways there. Okay, so there are a couple, when we talk about the parts of the wave, basically this is a repeating pattern. So from one point in the pattern to the point where it starts repeating, we call that a wavelength. So like it could be crest to crest, it could be trough to trough, it could go from here to here, but we usually draw it as crest to crest. And And so that is what we call the wavelength. And the wavelength is symbolized by a Greek letter. It's a small Greek letter lambda. And so lambda looks kind of like an upside down Y. Looks like that. So that's the wavelength. Okay. We also have the amplitude of the wave. So when you did your wave on a string, you changed the amplitude and that changed the height. So the amplitude is defined as the distance between the peak and this midline. It doesn't go all the way from top to bottom. It goes to this rest position. So that is the amplitude. And there's no special symbol for that. So we've got crest and trough and wavelength and amplitude. Okay. And then for longitudinal waves, instead of crests and troughs, we have these places where it's mashed together. So we call those compression or compressions. And there are places where they're spaced farther apart than they normally are when there's no wave going through the slinky. That is called a rarefaction. Okay, and so there's also a wavelength here is the distance from one compression to another. So that would be the wavelength lambda. Or again, you could go from rarefaction to rarefaction. Well, that's a really ugly line. And so in longitudinal waves, the definition is that the medium, or if you look like one part of the slinky, it's going to be moving back and forth as the wave travels. Okay, so the longitudinal waves are basically the medium moves parallel to the direction of wave travel. And one of the big things they kind of mentioned in the video was that waves carry energy. And so we'll talk about that in a little more detail at another point. So sometimes we know it takes a while for the slide to change. There we go. Alright, so we have speed, wavelength, and frequency. So what's frequency all about? So all waves are made by vibration, something happening over and over, or back and forth. So the number of vibrations per second is called the frequency. And the units are measured in hertz. Okay, so frequency, which is symbolized by a little f, is equal to vibrations, that should be a B, vibrations per second. Vibrations per second, and vibrations per second is equal to what we call hertz, Hz. Okay. So you may have seen hertz. People don't listen to the radio much. Sometimes you see those frequencies in hertz. You might see like megahertz or kilohertz or something like that. If you're a musician, you might be familiar with some of the with the frequencies of some notes, like middle C is 256 hertz. So if you play middle C on a piano, that string is vibrating 256 times per second. So that's the idea of frequency. The speed of a wave is how many meters per second it travels. Speed is always distance over time. Okay, so you know that the speed is always distance over time. And the relationship here, the question is, what does the speed depend on? And that's what we were doing with the wave on a string thing. So it turns out the speed doesn't depend on the frequency of the waves. It doesn't matter whether you're making a lot of waves per second or very few. Each wave moves the same speed. It doesn't depend on the amplitude. What it does depend on is what the wave is traveling through. Okay? And the material the wave is traveling through is called the medium. So in the video we just watched, the medium was the slinky. If you're talking about sound, you're listening to the sound of my voice, the waves are traveling through air, so the medium would be the air. Okay? And so the speed of a wave is determined by the medium, and the medium only. And you can change the medium like we did in the app we changed the tension on the slinky, or the tension on the string. Okay, that would change the speed of the waves. Okay, so the speed of the waves on the string depends on the tension on the string, and the speed of sound in air depends on the temperature, which is basically related to the density of the air. We usually just say it depends on temperature. So the speed of sound is actually greater the higher the temperature. So that's an important thing. Now, speed and wavelength and frequency are related to each other by an equation. Okay, and this is true for any kind of wave. And that means that we know the speed is equal to the frequency times the wavelength. Okay, so V is equal to the speed. We know that F, and the speed's going to be in meters per second. F is equal to the frequency, and that's going to be in hertz. And then lambda is equal to the wavelength, and that's going to be in meters. Now, if you wonder how we take hertz times meters and get meters per second, hertz, remember, is vibrations per second. So vibrations is just a number. There's really no unit on that. So hertz are really equal to 1/seconds. So when you take 1/seconds times meters, you get meters per second. Okay. So that's an important formula. We will use that a lot. Now, just about everything that I can think of that we do, the speed is going to be constant. If we're comparing things, we're always going to have them going through the same medium. So if the speed is constant, let's look at what happens to as you increase the frequency of the wave. So if we go here, and we're going to go to oscillate, and let's go to a no end, turn our damping down a little bit. Okay, and let's start at a low frequency. Okay, so as we can see now, so this wave has the same speed. It moves along. So if you're tracking the peak moves along at the same speed, whether we have a high frequency or a low frequency. So again, it'll be easier if we show this in slow motion. So that moves the same speed, the same number of meters per second, again, whether we have a high frequency or a low frequency. So if we're tracking that now, let me find a good time here. So it reaches the top, and so that peak is still moving along, even though the up and down motion is much slower. The side to side motion actually is the same. But what I want you to look at now is the wavelength. So if you look at this is a very long wavelength wave. As a matter of fact, we can't see a whole wave on the screen all at once. But as you increase the frequency, what happens to the wavelength? Oh, the wavelength looks to be shorter. So if we pause this here, so one wavelength would be from there to there. If we increase the frequency even more, the wavelength actually gets even a little shorter. Okay. So here here's another common thing that we run into. So as frequency increases, we know the wavelength decreases. So the fancy terminology for that is that they're inverses of each other. When one goes up, the other goes down. Okay, so we can use this formula. Let me do a couple quick example problems. Okay, so a student is making waves on a string. She moves her hand back and forth 2 times per second and makes waves that have a wavelength of 0.4 meters, and we want to calculate the speed of the wave. So looking through here, I'm going to be systematic. So 2 back and forth 2 times per second. That's a frequency. How often it happens. How many times per second? 2 times. So the frequency is equal to 2 hertz, or 2 waves per second. And we have a wavelength equal to 0.4 meters. And we want to know what is the speed. Alright, well, we don't have to be a mathematical genius to figure this one out. We've got the equation. We know the speed is equal to the frequency times the wavelength. So I'm going to take 2 times 0.4, which is going to be 0.8 meters per second. Okay. Now, even if she moved her hand back and forth faster, maybe 5 times per second, okay, the speed's going to be the same. The wavelength is going to get shorter, so that we would still end up with 0.8 meters per second. Okay, another example problem. Speed of sound in air is 343 meters per second. So a musician plays middle C, which has a frequency of 256 hertz, and we want to find the wavelength of those sound waves. So just looking through here, it looks like we know that speed is equal to 343 meters per second. We know that the frequency is equal to 256 hertz, and we are looking for the wavelength lambda. So if we say V is equal to frequency times wavelength, I'm going to divide with the letters first. So I would divide both sides by F, and we would get lambda as equal to the speed over the frequency. So I'm going to have 343 over 256. So 343 divided by 256. 1.34. So lambda is equal to 1.34 meters. Okay. Alright, so we should be able to use those pretty easily. Wait for the screen to change here. Alright, next was wave interference. Okay, so we want to see what happens when these waves are on the same thing and they meet each other. And one of the questions is, do they bounce off each other or pass through each other? So let's go to this example here on this pivot video. So if we show that, so they're going to make a wave. Okay. It's going to reflect off that end there and start coming back, and then they make another wave. So in the middle, those two waves meet. Okay. So the question is, do they bounce off each other or pass through each other? So I want you to look at that carefully. Think about that. So whether they bounce off or pass through. Okay, so if we look at it right there, so we have a wave over here. that is going to the left. So the up wave is going to the left and the bottom wave is going to the right. So if they bounce off each other after they meet, then the bottom wave will be going in the opposite direction and the top wave will be going to the right. Okay, if they pass through each other, then after they meet, the bottom wave will continue to the right and the top wave will continue on to the left. So let's see what happens. Take a close look at it. And so they've met, and now you can kind of see that after they meet, the top wave continued moving to the left, the bottom wave continued moving to the right. So they do not bounce off each other. They pass through each other. And after they meet, are the waves unchanged, changed, or unchanged? So let's go back to the beginning here. So what I mean by that are the amplitudes about the same before and after? So again, we'll play this. Okay, so look at that. So they're approximately the same size as each other. It's really hard to get a measurement. Actually, on this, we probably could get a measurement. Let's look at that. So if we look at this, put that on there. Okay, so that looks like they're about 5 units. Their amplitude is about 5 before they collide. And then we'll keep it playing, and then after the collision, not quite 5, but pretty close. Okay, and some of that is just damping that happens. So they go essentially unchanged. Okay, so now let's look at this in some detail. So what happens when they meet? We can end up with either constructive or destructive interference. So we're going to do a little bit with these diagrams here. So let me go through this. So this is t equals 0 seconds. Okay, and let's say that this one is moving that way, that one is moving that way. Okay, and each block moves one way, moves one block, each wave moves one block each second. So what that means is that at t equals 1 second, this one will have moved one block to the left, so it is now going to be over there, and this one will have moved one block to the right, so it is going to be right here. Still moving in the same direction that they were. Okay, and now is where things get interesting. So when we go to t equals 2 seconds, what's going to happen? Okay, well, this idea of superposition is that when they're in the same place at the same time, their amplitudes are going to add up. So each one is going to move one block. So that means that we're going to have, so the one, I'm going to do this in different colors. So this is going to be the one going to the, so the blue is going to be the one going to the left. Then I'll change this to red. So the one going to the right would end up being in the same spot. Okay, so overall, what do we get? We'll change it to purple because we have blue and red meeting. Okay, so each one has an amplitude of 1, so I take 1 plus 1 and I get 2, so that means the actual wave that we see is going to look like that. It's going to be 2 blocks tall. So if a 1 block wave meets another 1 block wave, when they interfere, we get a taller wave that's going to be 2 blocks. Now afterwards, okay, they are going to keep on moving. So the idea is that this does not make any permanent change in either wave. Just for an instant, they are like this. And then now, we're going to have the one block wave will be there. The other one block wave will be there. Sorry. And then they're going to keep on going as if nothing ever happened. And so later, the next second later, they will have each moved one block. In the direction that they were traveling. So this one continues to go that way, this one continues to go that way. And this would obviously be t equals 3 seconds, and this would be t equals 4 seconds. Okay, so this is what we call constructive interference. So constructive interference, you end up meeting and they're adding up. We're building something. So construction is building something. So destructive interference, let's look at this here. So this is t equals 0 seconds. Okay, so let's see if I do my color thing here. This one will move one block. This red one will move one block. Okay, that's t equals 1. And then in the next second, we'll have this one will move one block to the right, and actually I should do that as dotted. And the blue one will also move one block. It'll move one block to the left. So they're overlapping. And that means in reality, when they meet, nope, I did that wrong. I'm sorry about that. Take a second for the eraser to come up. There we go. Okay, so this one is the, go to the red here. So we have that. The blue one actually is downward. So we get that. So those two together. So when they add up, in reality what we get, we'll put that in purple. So you have one block up and one block down. They cancel each other out. And so for an instant, it's as if there's no wave on there. All that we would see is just a straight line. Okay? And then afterwards, they continue on as if nothing ever happened. So we have one going to the left, we have the other going to the right, and again it's as if nothing ever happened. So t equals 2 and t equals 3. Okay? So that is destructive interference. So they, I'm going to say cancel out, but cancel is only temporary. Okay, so it's just for an instant they look like they canceled out. Both waves are still there. It's just for that instant in the superposition, it looks like nothing is there. So if we go back to this video and let's go ahead and take that off. We'll go back. So you can see that for just an instant, it looks like there aren't any waves on the spring. So we'll go frame by frame here. So they are meeting, they are undergoing destructive interference, so right about now, and there. So for just an instant, it looks like if you just take that snapshot, that one frame, it looks like there are no waves on that slinky. But if we keep going and advancing, we see that both waves are still there. So that is wave interference. Okay? And then our last slide, so constructive interference, is, we'll just write that down again. Okay, so this is where the amplitudes add up to a larger wave, and destructive interference is where the amplitudes cancel out to a smaller wave. Alright, that concludes our Wave Basics screencast.